All right, welcome everybody to our Let's Talk Meshing webinar. In this webinar, we're going to be talking about a land speed record attempt using high-fidelity, high-speed CFD. So allow me to introduce the presenters for this webinar. First is Andy Liu from TotalSim. Andy graduated from the University of Southern California with a bachelor's and master's in aerospace engineering and aerospace design, respectively. He then spent 6 years working for Swift Engineering, where he performed CFD for aerospace and automotive applications, and this included a billion-cell automotive calculation as well as a passing maneuver simulation. Andy now works for TotalSim and helps to further their aerospace capabilities using tools such as OpenFOAM and Pointwise, and Andy's actually the one that generated the grids and ran the calculations that we'll be showing off today. My name is Travis Kerrigan. I'm a senior engineer here at Pointwise, and my responsibility is to work with clients and help strengthen their CFD process by introducing Pointwise into that process. And I do this by developing either interactive solutions using our software or automated meshing solutions using our Glyph scripting language. I'm also active in a lot of marketing activities like webinars such as this, videos, as well as attending conferences. So before I pass things over to Andy, I just wanted to mention that the purpose of this webinar is to really showcase how the Spirit of America team inexpensively uses CFD to assess the performance of their vehicle. And such preliminary CFD studies really help to uncover trends like those that Andy's going to be talking about in the results section of this webinar. And early in the design, these are really critical for the design and optimization of the vehicle. So with that, I'm going to pass things over to Andy, and he's going to begin by talking about the history of the Spirit of America. So Andy?
Thanks, Travis. So for those of you who don't know, the Spirit of America was one of the first cars to jet-propelled cars to set new land speed records. Now the first car, piloted by Craig Breedlove, set the record at just over 400 miles an hour. And then in the subsequent years, there was a little bit of back and forth until Craig set a new record in the vehicle pictured below, and that was set at just around 600 miles per hour. Since then, looking into modern day, the latest land speed record was set back in 1997 by a British group in the vehicle called Thrust SSC. The team was led by Richard Noble and piloted by Andy Green. In the last couple of years, Craig Breedlove has kind of expressed a desire to sort of retake that record. So he's been heading up a new team, also called the Spirit of America, and the chief aerodynamicist of that team is Neil Roberts, and it's going to be piloted by an F-16 pilot named Mark Zwick. The intention of the new vehicle is to set the record at over 1,000 miles an hour, so hopefully something that will stand for a long time. And one of the new developments in this iteration of the Spirit of America that wasn't available before is the advent of CFD. And so the hope is that we're going to be able to assess the performance of the vehicle before it actually hits the salt flats, and also do some preliminary design and optimization, and then finally also understand kind of the safety and stability of the vehicle itself. So a little bit about us. I work with TotalSim. Our UK office was kind of born out of racing. Over the years, they've been associated with a lot of different F1 teams. And then in 2007, they established their own group. And then in 2009, we established the US office over here. So our US office is actually based out of Columbus, Ohio. And can we go to the next slide? Yes. So we're based out of Columbus, Ohio, and we've got about 11 guys on staff. In-house, we hold about 576 cores that we do a lot of our computations on. But if we do need to scale up, we have a 10 gig FiberNet connection down to Ohio Supercomputer, and there we can leverage over 14,000 cores, and that number changes all the time. Our president is Ray Leto, and he's got about 20 plus years of experience in the racing world, both as race engineers and team leads as well. And then our technical director is Nathan Eagles, who was, who started the CFD department at Williams F1. So we've got a pretty good group of guys and pretty good, power in-house. So that kind of that's a little bit about us. And then I'll hand it back to you, Travis.
All right, thank you, Andy. So right now we're going to spend a little bit of time talking about mesh generation. Andy created these grids for the study and then ran the calculations. And when we decided that we wanted to do this webinar, he passed them along to me. We sat down, we dissected them, and we kind of uncovered a few things that we thought we'd share about the process. The first thing being organization. So when Andy imported the Spirit of America into Pointwise, there was a lot going on. There's a lot of surfaces, there's a lot of quilts, models, just a ton of entities in the display. And this is true of complex geometries. When you import things like this into Pointwise, there can be a lot of things going on. So it's really beneficial if you spend some time up front, not only cleaning the geometry, but cleaning it in preparation for organization, again in preparation for your surface and volume meshing. So that's exactly what Andy did. He spent a little bit of time cleaning up this geometry. In the first image, you can see each color represents a different surface or a different quilt or model in the geometry. He then selected everything and assembled this into a single watertight solid in that second image. Now, if you had multiple parts in an assembly, you would have multiple solid models, but in this case, it's a single part, it's a single solid model. And the benefit of having a watertight solid is so that surface meshing can be automated, very automatic. You can create a surface mesh on this model in as little as one click, and it'll be guaranteed to be watertight as well. Now, as part of this process of cleaning up, it kind of helps to organize, because after you have your solid model, the next step is quilting. And quilting allows you to basically define what the surface mesh topology is going to look like before you even create a surface mesh. So different quilts represent different logical meshing regions, or where domains would lie on the geometry. So you can see that he's quilted this up. So he has a quilt for the fins, the fuselage, the intake, etc. And again, the benefit is when he meshes this, each quilt gets its own domain, and quilt boundaries basically become the locations of connectors. So this process of cleaning up further helps to organize and simplify the geometry that he'll be working on. Now, along the organization, the next thing is using the layer manager. The layer manager is a fantastic way. It gives you the ability to isolate and operate on entities without having anything else going on. Reducing clutter is kind of its primary role. So you can see he's created a number of layers for construction entities, a number of layers to hold the geometry like the model and the quilts. He can isolate these. In this image, you can see he's isolated the connectors of the vehicle, so he can operate on them independent of anything else. And he's got a number of layers for the different blocks in the volume mesh, so he could isolate those as well. So layers are really beneficial when it comes to organizing your grid system. However, an entity can only exist in a single layer at a time. So beyond organization, you can't really use them for an efficient means of selection. To do that, you need to go to groups. So groups not only provide an additional way to organize your geometry in your grid system, but also to provide an efficient way to select multiple entities. So for example, Andy's created a group for the fin domains. He can select that group. It'll automatically select all the fin domains, and in this image, we just changed the color. But he could easily bring those into the grid solver and change some unstructured solver attributes if you'd like. Okay. So if you find yourself performing specific operations on a set of entities frequently, it's really beneficial to create a group. Not only for organization, but also for selection purposes. So at this point, he's cleaned up the geometry, he's organized it, and now he's thinking about creating that surface mesh. And I mentioned before, creating the surface mesh can be done in as little as one click. You set up some defaults, you select your model, you create an unstructured triangular surface mesh. But what Andy wanted to do is he wanted to reduce the cell count on the surface, get some nice flow-aligned elements, help resolve curvature, and do this using structured meshing. Okay? So what he did is he identified very easily some quad-looking quilts on the surface and just deleted the unstructured domains and created structured domains in their place. And again, the idea here is you can see for the lip that these efficiently are able to resolve the curvature of this intake lip without using nearly as many cells as the triangle equivalent would. Imagine diagonalizing each of these quads, you would have 2 triangles per quad. And if you can further imagine, in the volume mesh, as we extrude off of these, we would get hexes that are relatively flow aligned. He did the same thing for the intake strut as well as the top of the fin, just identifying these rectangular looking patches, deleting the unstructured domains, and replacing them with structured domains. Now, one thing to keep in mind when you're doing this is that you want the transition from structured to unstructured to be as smooth as possible. So you can see up here that these quads are roughly the same size as the triangular elements, and this is going to help when T-Rex is used, or when you're using T-Rex to create your boundary layer portion of the mesh. Another area where Andy elected to use structured meshing was the exit of the engine compartment, this tubular structure, and typically what we recommend for things like this is a butterfly topology or an OH grid, which you can do in as few as 5 structured blocks. The benefit there is you can run it through the elliptic solver, you get good orthogonality, flow alignment, and that topology supports boundary layer control. So you can continue to cluster elements in the boundary layer region. And then you could propagate this downstream as far as you would need it to capture any additional flow features that you'd like to. The last region where Andy used structured meshing was outside of this near field hybrid block that he created right around the vehicle. Inside that block, it's going to be using T-Rex to generate the volume, but outside that, it was relatively simple, and he was able to assemble some structured blocks that were flow aligned. You have good quality hex elements with a reduced cell count. So once everything's been organized, he's got his surface mesh, he's replaced the domains that he would like to with structured domains. The next step is to populate that inner hybrid block using T-Rex. And T-Rex stands for anisotropic tetrahedral extrusion, and we've talked about it a lot. And the reason we've talked about it a lot is because it is a fantastic way to automatically create boundary layer resolved grids. Traditionally, the way it's worked is it would work off of a triangular front. We would advance points, create these stacks of right-angled tetrahedra. So in this example, we're advancing a point and creating a fan of right-angled tets. These points would be checked, or the elements would be checked against quality criteria that the user could specify as well. And if a point violated that, it would stop locally, but continue advancing everywhere else. And once the entire front was done, and you have these stacks of right-angled tets, we would combine them on export into triangular prisms that transition very naturally to an isotropic tetrahedral far field. Okay. Now, all of this is controlled through just 2 panels. There's the number of layers you can specify, the growth rate, some quality criteria, and then over on the right, the boundary conditions for T-Rex. And the primary thing that you'd be specifying here is your initial spacing in the boundary layer region given the Y+ value that you'd like to achieve. Now, how did we handle quads? Well, if you had a quad domain in your mesh, what we would do is we would insert a pyramid that had the same height as that initial spacing you'd specify. And that basically presents T-Rex with a collection of triangles because each pyramid would expose 4 triangular faces, which we would then pass on to T-Rex and march right-angled tetrahedra off of. And then after combination, we would get triangular prisms, but in the first layer, you would still have these really high aspect ratio pyramid elements. And it turns out solvers tend not to like those very much. So we had to think of a new way to handle marching off of quads using T-Rex. And what we came up with was another approach for creating pyramids off the surface. So what we do is we create a pyramid off the surface that's half the height that you specify, half that initial spacing. We then create 4 side pyramids around that that have the height of the spacing you've specified. And this creates a topology that has a divot in the top. And we fill that with 2 cap tetrahedral elements. Now if you combine all of these, you get a hex in the first layer. But what this does is it exposes 2 triangular faces per quad, which we can then march right-angled tetrahedral elements off of. So to kind of illustrate this, these images were taken with Insight. You can see we've got a quad surface mesh. We've inserted some pyramids. We put in the base pyramids and the 2 cap tets, again exposing 2 triangular faces per quad. We then advance right-angled tetrahedral elements off of that, and then as a post-processing step on export, combine these into unstructured hexahedral elements. Now the benefit is that if you have a surface mesh that consists of quads and triangles, you use the same parameters in T-Rex, those same 2 panels, and you get the advancement, and then afterwards on export we'll combine into unstructured hex elements and triangular prism elements that are point and face matched at their interface, all automatically, that transition naturally to isotropic jets in the far field. So to show you what this looks like on this model, you can see the complexity of the surface mesh, and T-Rex marching, it's able to navigate these concave corners very easily, march out of this concave corner formed by the fin and the fuselage. And then down here you can see the surface mesh with triangular elements as well as quads. You've got the triangular prisms transitioning to hexahedra as it wraps around that intake lip. The final grid, or the final cell count for this grid, was about 30 million, 4 million hexes, 8.5 million tets, and 17 million prisms. The reason we had more prisms in this mesh was because the surface grid consisted primarily of triangular elements. Now, this grid took Andy about a day and a half to create from start to finish. Actually, initializing the volume mesh with 30 million elements only took a few minutes on a laptop, but it's the process of cleaning up, organizing, creating that surface mesh, deleting the domains that you would like to replace with structured domains, that whole process, and then combined with the initialization was about a day and a half start to finish. Now, that volume mesh was relatively isotropic. There's not a lot of control out there in the initial mesh for capturing things like shocks that accurately. So one of the things Andy found is that, as this vehicle is traveling transonically, supersonically, you're getting shocks, and to capture these things you need additional refinement in the volume mesh. And to do that, we recommend using a baffle. A baffle is basically a way of explicitly placing points in the volume mesh for additional refinement. So when Andy ran this calculation, he found that shocks were forming. He was able to export some iso surfaces of Mach gradient from his post-processor, import them into pointwise as STLs, then sketch unstructured domains on these STLs and extrude them to create prism blocks. And so you can see there's a number of prism blocks in this volume mesh. He added them to the block definition for additional refinement. And here's a cut through the symmetry plane. You can see that the additional refinement provides a way to accurately capture those shock structures and get a more accurate solution. So with that, I'm going to pass things back to Andy, and he's going to start by talking about setting up the boundary conditions for CFD++.
Thanks, Travis. So like you just mentioned, these solutions were run in CFD++, and that's a commercial software written from Metacomp Technologies. So here's kind of a basic layout of how the boundary conditions were set. Because we generated a viscous grid with boundary layers, we were able to set the majority of the vehicles as a no-slip wall. And then subsequently we had the rotating tires, front and rear set, which were modeled as no-slip rotating walls. The customer actually provided us with some of the engine specification data, so then we were able to, so we knew what the anticipated static pressure was supposed to be at the engine inlet, and then the engine exit was just a mass flow matched boundary condition. Then finally, because this vehicle sits pretty close to the ground, we found it necessary that to set the floor as a translating wall. And this isn't necessary for all vehicles, but because we anticipated that there might be some ground boundary layer effects, this was the reason that we took that approach. Getting into some of the results, here we've just plotted the lift and drag of the solutions through the Mach sweep. One thing you'll notice is that we've done kind of a coarse sweep, and the reason being is that this is kind of the first pass CFD iteration. So the purpose is to just get an understanding of what the vehicle is doing, and not so much populate an aero map of the vehicle. So you can see we've done essentially a Mach 0.1, 0.85, 1.15, 1.4, and this gives us from a compressible range all the way up to the supersonic regime, so we can kind of understand how the flow develops through the speed range. Additionally, we've actually run some beta points, which you may or may not be able to see in the plot. The points are pretty much on top of each other. The reason being is that we're anticipating that the yaw or the crosswind that the vehicle sees at high speeds is going to be pretty low because crosswind versus the free stream velocity is going to be a very small angle. Now, two things of note on this plot. One, we've got the lift trending downwards, meaning that we're generating downforce and we're keeping the vehicle on the ground, which is always a plus. And two, just as we anticipate, the drag increases exponentially with the with the velocity, with the free stream velocity. And I haven't shown it here, but if we non-dimensionalize the drag by to drag coefficient, we can see that there's a large drag rise through the transonic region, and then a gradual drop-off as we get into the supersonic regime. So getting into the fun part of CFD, post-processing, what we actually use at TotalSim is a suite that we sort of wrap around peer review, and it mostly consists of function objects and Python scripts. So to give you an idea of some of the stuff that we handle for our post-processing, on the bottom left we've got a couple images here that we call drag or force X-rays, and what we do is we actually generate a plane on one direction of the vehicle. For example, on the very bottom left image, we've generated a plane behind the vehicle, and we've just collapsed all the pressures onto that particular plane. And what you're seeing is the net pressure signature on that plane, and that sort of helps you eliminate regions that are generating, drag or downforce or lift. It depends on what plane you're looking at. In the middle, we've got your very standard slice components, where we just take axial slices through the vehicle, and they could be transverse along, side to side on the vehicle or up and down. It doesn't really matter. You can specify the direction as you wish. And there we've just colored it by CPT. On the top right, we're looking at color contour on the surface, the very standard images. Here we've actually colored it by CPZ, which gives you kind of a measure of what areas are responsible for lift and downforce. And then finally, on the bottom right, that's drag accumulation plot. And again, you can specify different axes. It doesn't necessarily have to be along the x-axis, but you can see how drag either accumulates or is distributed along a particular axis of the vehicle. And this isn't exclusive to what we can do in our post-processing capability. We obviously have some more, but this is just kind of a small taste of some of the things that we do. So in this particular image, we've generated these images automatically through our scripts, and in this particular one that you're seeing, we've colored the surfaces by skin friction coefficient, and what you're seeing in the red cloud is the isosurface of total pressure. Total pressure. And this is a Mach 0.85 case, right? So we're not expecting to see a lot of strong shocks all around the vehicle. What you're not seeing from this particular view there are some shocks that are happening underneath in the diffuser of the vehicle. But if we go to the next one, this is colored. This is the same condition, but it's colored by CPX, and it's sort of a measure of pressure coefficient with respect to the x-axis. So to simplify things, warm colors in this picture mean areas that are generating drag, and cool colors mean areas that are generating negative drag, or so to speak, thrust. Along the nose, you'll see that there's a lot of red and yellow, and that's pretty much anticipated with a lot of stagnation pressure. And then the same thing along the lip of the intake. And then for the rest of the vehicle, it's pretty much clean. Around the back, where you might see some reversed flow, there's a multitude of colors. There's some red, and there's a little bit of green there as well. But in the next image, in this transonic case, or lightly supersonic, a lot of the red has kind of disappeared off the nose, and that's mostly due to the wave drag that's being generated from the shocks. What you're not one of the reasons that you're not seeing, it's difficult to visualize the shocks with CPX. It's not the best metric to view it. So what we've plotted in the next image is skin friction coefficient, but with a tighter tighter band, right? And right away you can kind of see the large area discontinuity on the nose, which is a pretty significant signature for where a shock is being generated. Elsewhere along the vehicle, you can see some happening around the fins, behind the fins, and then a little bit underneath, which again is difficult to see from this image. But it's but again, so the idea is that we're trying to anticipate where the shocks are happening. So we can go to the next image. All right, so going back to now what Travis mentioned about generating baffles. The point of this particular CFD exercise is to anticipate, to try to determine where the shocks are being generated. We weren't so much as interested in how far they propagate, because this thing is supposed to be running on the salt flats, so propagation really isn't an issue. The issue is determining where they happen. So because we didn't necessarily have a mesh adaptation, automatic mesh adaptation algorithm available to us for one reason or another, we kind of had to take a sort of rudimentary approach. So like Travis mentioned, we ran an initial solution, and from that initial solution we looked at gradients of Mach. And using that, we were able to kind of anticipate where a shock might be generated, and that's how we plotted, or that's how we determined where to generate the baffle faces. Now with the refined grid, this is kind of the solution with the Mach gradients plotted into the isosurface. And you can see the areas of high density in kind of the local block. That's exactly where we've generated the baffles. So the approach that we took to, so to speak, refine the mesh or adapt the mesh ended up being rather successful in this case, because with this, it helps us better enable us to see where the shocks are being generated. Again, we're only interested in where they're being generated and not so much how far they propagate. So finally, this is just a couple more images to kind of to finish out the solution. Again, we're looking at skin friction coefficient here, and this time we've actually added onto it a surface streamlines. So in this particular view, you're looking at the bottom of the vehicle, and like I had mentioned before, you see some discontinuities along the underside, especially in the diffuser area between the rear wheel strakes. One thing of interest is that with the surface streamlines on, you can actually see where the vortices are being generated off of the front wheel well, and these vortices kind of extend along the length of the diffuser, and that just serves to help generate some downforce, keeping the vehicle into the ground. And so finally, just kind of a pretty picture to round out everything. Again, this is skin friction coefficient on the vehicle, and this is sort of the less cluttered, I should say, less cluttered is kind of an understatement, or overstatement, I should say, version of viewing the Mach gradients along the vehicle. And so, yes, this kind of gives you an idea of where the shocks are happening again. And what you'll notice is as it gets out to the far field block, it quickly dissipates. And again, just kind of wanted to run home the fact that, again, we're not so much interested in where they propagate, but more so where they're being generated. So in conclusion, after doing this study, one, we found that the CFD results that we got were showing us reasonable force trends on the vehicle. So the drag and the lift that we were expecting to see on this vehicle, we can take, obviously we'll take it with a little bit of grain of salt, but it just goes to show that the mesh approach and the setup approach that we used for this particular exercise is I would say adequate. The baffle refinement approach that we used to determine where the shocks were happening was, again, a valid approach. It allowed us to see exactly what we were looking for without going too crazy into analysis. And finally, the force numbers at the high Mach solutions just kind of implicate that we've got a little bit of work to do. A little bit of optimization might need to be done on surfaces, but with that, we'll just do a small redesign of the vehicle and get ready to look at the next iteration in CFD.
All right, thank you very much, Andy, and thank you all for attending this webinar. I just want to mention before we open it up for questions and answer session, the recorded video will be available as soon as May 1st, as early as May 1st. You'll be able to access that from pointwise.com/webinar as well as on our YouTube page. If you have any questions about Pointwise or how it was used in this particular study, please feel free to email me. If you have any questions about TotalSim, the work they did with this, and their post-processing suite of tools, please feel free to email Andy Liu. I'm going to leave this up during the Q&A session, and we'll open that at this time. If you have questions, just type them into the questions dialog box, and we will answer them at this time. We'll leave it up for a couple of minutes so you guys can type in some questions. Okay, Andy, here's a question. You can unmute. All right. So the grid was 30 million elements, and you ran the calculations with CFD++. How long did the calculations run, and what was the hardware?
The hardware that we ran on were, oh gosh, this might be a better question for Ray. He's kind of our in-house IT guy. I think they're equivalent to like Intel Westmere chips. Mm-hmm. Not the latest and greatest, but also not exactly obsolete either. The solution duration was about, I think it was about 12 hours to get about, I think 1,500 iterations.
Okay.
Yeah.
All right. So we got another question. Are the post-processing scripts that you developed for ParaView open? Or are they shareable?
Yes, they are. I mean, we have some. Generally, the way that we share them is through, working with certain clients. So I would be remiss to say that we go around and share them with everyone. But if you'd like to contact us about it, I'd be happy to field some more questions about them.
Okay. Here's another good question. Did you find there were any trade-offs in the number of baffles you defined versus the processing time?
Yes and no. Obviously, with more baffles, we're adding in more cells, right? So then the time did go down. But if we didn't care so much, I mean, without the baffles, we were still getting the shock signatures, mm-hmm. but it was a little bit coarser and a little bit difficult to kind of pinpoint where on the surface they're being generated. Right. So again, so the answer is kind of yes, kind of no. I personally thought that adding the baffles back in, and I try to track down almost all of them. Adding the baffles in was a better approach, gave us better fidelity answers.
Okay. Would you say that maybe adding the baffles in could allow you to maybe coarsen up some other areas of the mesh where there wasn't a lot of influence? So ultimately you would maybe end up with the same cell count or maybe not much more than what you started with?
Oh yeah, I think so. especially in the local block. I mean, we probably could have dropped or upped the growth rate so that, and then up also the max cell size so that, like you're saying, we could probably trade off some local free stream cells for baffle refinement.
Right. Okay. Let's see. Could you talk about what turbulence model was used for the simulation?
This is just a standard K-omega SST.
Okay.
And that was just kind of out of the box from CFD++.
Mm-hmm. Do you recall what Y plus value you used?
It sort of ranged, especially for the lower cases. We were using Y plus 1. That's low Mach. Obviously, as you get higher and higher through the Mach regime, you've got to get tighter and tighter grids to get Y plus 1. So then we started using wall functions for the supersonic case. So roughly about Y plus 30.
Okay. Now this was a preliminary study. So have you guys performed any optimization yet, or have you started talking about it?
No, not quite yet. Again, this is kind of driven by the customer, and the customer is sort of taking a little bit of time to digest the data. Additionally, they're still organizing themselves. So again, so like I said, it's a prelim study. They've got some work on their end to do, and we're just facilitating their design study.
Okay. Here's a question. They want to know how the unstructured hex elements are developed, and I may need to back up the slides a bit to that part. So the unstructured, just to recap, the unstructured hexes are developed by placing pyramids in that first layer that are half the initial height. You place some base pyramids around all four sides, and then 2 cap tets. This alone, now this base pyramid that's on this triangular face of the prism or pyramid is missing, so you can see that. But those elements right there form a hex in the first layer after we combine. Now, in T-Rex, we're not combining the elements, so these 2 triangular faces are then used to stack right-angled tets like we normally do. And you can imagine joining those right-angled tets, you join 6 of them, you get a hex. And so that's exactly what happens, is that base collection of elements becomes a hex, and then the collections of right-angled tets on top of that become hexes for the remainder of the layers. So that's how that works. There. Okay, let's see. So one question is, how are such big projects handled? Say if one wanted to go back a number of steps, are there a limited number of undos? Maybe you could expand upon that question a little bit. Are you talking more about the meshing? Because if you're talking the meshing side, I think in point-wise the max number of undos you can specify is like 20. So as you're generating the grid, you can back up. Obviously, we recommend saving at various stages as well. Do you have anything to say about that, Andy?
Yeah, so kind of along with the organization that you had mentioned, there were a couple times where I did have to backtrack because I would kind of go off in the wrong direction as far as generating the kind of grid that I desired. So having everything organized in very concise manner did really facilitated being able to backtrack and go forward. One of the big steps is really getting your surface mesh to the point that you want it, and so I think that's a giant milestone right there. Having everything organized up to that, especially saving that out, and then and then moving forward from there. I mean, because there's a ton of different ways that you can generate your volume mesh. So yeah.
Okay. Another question is, why combine tets and pyramids to form hexes in T-Rex rather than directly? Well, right now, in point-wise, a block can only consist of a single element type. So other than the fact that you can have a quad face and an unstructured block, that's kind of a special case where we put a pyramid in that first layer. So right now, an unstructured block is all TETs, and so that's kind of why you do that. But also the other thing is when you decompose those elements, you end up with collections of faces that make it easier to stitch together with other faces. And when you combine those into hexes, you can kind of perform all of those operations. Whereas if you're creating these hexes directly, which ultimately the plan is to do something like that moving forward. In version 18, those of you who have maybe heard us talking about Pointwise version 18 at our user group meeting, these are the kinds of things that you may be able to expect in that version. So, but generating hexes directly, you kind of lose that because now all the faces are quads, and so being able to stitch them together becomes a little bit more of a challenge. That's a good question. Let's see. Okay, in cases like this, do you simulate the whole geometry or just half of it due to symmetry?
Well, because we ran some crosswind simulations, we had to do the whole. For the straight-on zero yaw cases, especially for the low mock, we went ahead and we ran that symmetry. But you can, there's a couple ways that you can generate the mirrored mesh. You can do it in Pointwise. CFD++ has its own tools. It's pretty trivial to mirror the mesh and do a full solution.
Okay. Let's see. What's the basic geometry model required to start meshing? Well, you actually don't need geometry to start meshing. In Pointwise, you can have a grid without geometry. Obviously, it helps if you have a geometry so you can project things properly. So there's one simple answer. You don't need geometry to mesh. If you do have geometry, it can come in a variety of different formats. You can do discrete formats like STL and Vermal, analytic open formats like IGES and STEP, and then CAD formats like SolidWorks, ProEngineer, CATIA, things like that. So you can bring those directly in. We have native CAD support, native CAD readers. You can import those and start operating on them. Let's see. Okay. Was there a plot showing lift versus speed, and did it show Mach speed independence? Yes, there was a plot. You want to mention something about that?
I don't I don't see there's much more to talk about. This is exactly what we plotted. Lift versus Mach right here.
Okay. And then just maybe you could recap. Was there some lateral stability analysis done, and if so, what did it show?
Yeah, so we did do a little bit of lateral stability analysis. I don't remember the yaw numbers off the top of my head, but it was essentially self-correcting. The fins that Neil provided on the rear of the vehicle were sized large enough so that we did have at least the correct direction of yaw, and yeah, that's about it.
Okay.
Also, the crosswind conditions that we looked at, they're all less than 1 degree, so they weren't super aggressive, right? So it wasn't it wasn't that we would see crazy numbers in those yaw conditions.
Okay. How did you estimate the size of the far field boundary, and did you use anything to avoid signal reflection from the far field?
So for the first pass, the far field was kind of just sized for an incompressible type problem. That's obviously oversized for, at least upstream, oversized for the supersonic case. But CFD++ has a Riemann solver that's built in for its far field. It also has some far field damping parameters that you can set. We opted not to. probably should have, I suppose. But in general, though, the like I said, the upstream far field for the high Mach cases were oversized, so I don't feel like those were necessarily required.
Okay. Let's see. Okay, this is a good question. Doesn't the lift versus speed plot show the car getting pushed into the ground as speed increases? What design change would you make to fix this?
Yes, it does. I guess one of the issues is that generally when you're looking at shocks, you want to look at sort of a zero lift condition, right? But at the same time, we're also looking for driver safety, right? So, you know, we could. There's a couple of approaches. I mean, there's lift being generated off of the contours of the fins, the side fins, I should say, and also we're generating some, actually not lift, downforce being generated in the diffuser, and you know, we could always kind of drop the we could raise or drop the level of the underbody, and we can always kind of angle the fins on the side to help you know, generate additional lift or downforce, you know, just kind of as we're looking to be.
Okay. Were there skin friction plots shown for higher speed cases? Let's go back here.
Well, I guess it kind of depends on what you're looking for, higher speed. If we're talking about the highest speed that we ran at the 1.4, I have those images. They're just not in this presentation. Not for any reason that, but you know, because I had spent more time generating these 1.15 Mach cases, or at least the images for them, you know, I figured I'd share these a little bit more in depth. Not sure if that's high enough speed for the.
Yeah, maybe would those be something that you could share if somebody contacted you?
Yeah, I believe so.
Okay. And yeah, the question was, there were some cases that you ran with a Y plus of 30 or above, right? You said that the higher speed cases you ran with higher Y plus?
Yes.
Okay.
And again, and that was really an interest of saving grid size and computation time.
Okay. Well, yeah. In terms of the skin friction for the higher speed, those of you who are interested, if Andy's able to share those, you can contact him at that email address and connect up. Okay. Any additional questions? All right. If not, then we'll go ahead and conclude this webinar. And like I said, we'll get the recording up. You can visit pointwise.com/webinar to see that, or visit our YouTube page to see the recording. And if anything comes up, our email addresses are listed on the screen. Give you another second to jot those down. And thank you all very much for attending our webinar this morning.